All right, welcome everyone to this webinar sponsored by the Chicago DOE Alliance Center. And to kick off our new season of webinars, I'm delighted to introduce Isaiah Jinhyuk Lim from the Department of Physics at the University of Florida. Isaiah is an experimentalist who's working in a variety of problems in materials or systems under pressure. His most recent and his early work focused on pressure effects on superconductivity and electronic and magnetic phenomena, but he's also worked on molecular systems and explored chemistry under pressure. In fact, he's been quite prolific. He has some 28 papers, despite this being fairly early in his career. Isaiah has a PhD in physics from Washington University, which he received in 2015. He's working with Jim Schilling, who's with us. He then moved to Washington State University, where he worked with Jinhyuk and explored physical chemistry and chemistry under pressure. And in 2019, joined James Hamlin's group at the University of Florida, again, as a postdoc. And we're delighted to have you give this talk with this very exciting title, Pressure, a Pathway to Advanced Materials. Over to you.
Thank you. Thank you for nice introduction for us. And yeah, I'm Isaiah Lim. Today I will talk about pressure as a pathway to make advanced materials. So I'm not boldly claiming that I made advanced materials, but I think the pressure is opening the new way to make advanced materials. So I will start with acknowledgement that my current research team at UF, and especially my current advisor, James Hamlin, here for his tremendous help and support for my research, and also my collaborators from CDAC, UIC, and especially CDAC. I was the CDAC supported PhD students in Jim's lab. So I was always thankful for that. And also I would like to thank the Be₂Re scientists at the Advanced Photon Source and Vora from the UAB and my former research group at the WSU. And also I give my sincere thanks to my PhD advisor, Jim Schilling. Okay, this is my outline of the talk. So I will talk about general introduction for pressure and why we use pressure for the study. And I would heavily talk about the diamond anvil set, particularly the resistivity technique that to test the superconductors. And I will talk about the two research results. The recent one is the dense loads rich superconductors, and my first postdoc research about the hydrogen storage and under pressure. So in my viewpoint, every material in the universe is under pressure. So I will say about what is this later. The pressure, by definition, is simply force divided by area. So it's basically force affecting on the surface of the materials. And you can say pressure might be the confining force of the materials, which governs the material's properties tremendously. And this is Earth, and we are here in Florida. So you will see the Florida, and then we are now in one atmosphere, 1 bar, but this is not that low pressure when you consider the 15 pounds per inch square. So it's like you are having some dumbbell on your head, or the dumbbell is pushing you everywhere. So when you go to the internal structure of the Earth, you will find much higher pressure. So center of the Earth is estimated 3.6 billion atmosphere. And so throughout this earth, every material is under pressure. So without pressure, we cannot study these materials. And not only that, when you go to the other planet like Jupiter, which is composed of mostly hydrogen and helium, that it has a much higher pressure, like a 40 million atmosphere at the center. And even the hydrogen itself is the estimated to be like the liquid metallic hydrogen in the pressure regime. And so when you want to study Jupiter, you need pressure. And not only that, the neutron star has the tremendous high pressure at the center that is estimated 10 to the 30 bar. So when you study the universe, yeah, you need pressure. And pressure can tune the energy of the materials, the system. So this is the fundamental thermodynamic variable. Pressure is very related to the energy of the system. And this is the energy landscape diagram that you are seeing here is just the example that the one system can have ground state and the metastable state. So you can explore these with pressure. So at low pressure, the bottom graph is for the graphite. And at low pressure graphite is the ground state. And when you apply pressure, this energy level changes and energy landscape changes. So when you apply pressure and then with the help of the high temperature, you can go into the diamond state, which is the ground state at high pressure. So you will get this beautiful diamond with pressure. So you can tune the energy of the system by applying pressure and get advanced materials, for example, like diamond. So now I will talk about the experimental methods. The diamond anvil cell, I think this is high pressure community. So everyone is familiar with diamond anvil cell. And I will go fast with this subject. But why we use diamond anvil cell? Simply, diamond anvil cell can generate very high pressure for study of high pressure materials. And so we need two diamonds in the cell, and then there's a metal gasket with a hole, and there's a sample nicely inside the pressure chamber, and pressure marker, and the pressure medium. So this is the simple version of the diamond anvil cell. The important part is that when you apply only 100 atmosphere on the cell, you can generate 2 million atmosphere on the tip of the diamond because tip is very small. So according to this equation, you will get very high pressure. And not only that, the diamond also has transparency. So it's very good at the spectroscopy measurement. So how we measure pressure? Yeah, I think everyone knows in this high pressure community that we mostly use Ruby, and also we use diamond anvil Raman for the higher pressure, and we use the gold or the well-known pressure marker for well-known equation of the state for X-ray diffraction measurements and so on. And what I like to emphasize is my expertise in this electrical resistivity setup in diamond anvil cell. So again, this is the diamond anvil cell. Inside, there's a bunch of wires coming out. And when you zoom in, you see this a little bit looks complicated, but it's simple that the 4 wires mostly coming out of this pressure cell. And when you zoom in, that there's a bunch of the electrodes on the gasket with the Scotch tape held. And when you close this cell and looking through the upper diamond, you will see the clear 4 electrodes touching each other. At the center, there's a clear separation with each other, the electrodes. we use a platinum electrode. Is the best for the electrical resistivity under pressure. And nicely put the sample at the center and then ruby beside. So this is the best setup so far. This is one of my best setup for the electrical resistivity setup for platinum beryllium 5. And we use bundle for geometry to estimate resistivity out of resistance, and to compare how difficult this setup is. You can compare with the human hair side by side. That everything is small. Basically, the sample is smaller than hair and ruby and the electrode and so on. And this gives you a challenge to set it up, this kind of measurement in the diamond anvil cell. But one could do it when you have this special tool that I can introduce. This is something I use heavily, and my precious one is my eyebrow hair. So I use this one to set up all these measurements. So this is my secret of the business. And for graduate students in the audience, I would like to advertise the YouTube channel that teaching how to set it up, the electrical resistivity measurement. But in this talk, I also briefly showed how to make the electrical resistivity setup. So this is being recorded, this talk, so one can follow this step. So we need diamond and gasket at the center, very nicely center diamond, and then gasket, and then we put the electrode on top of the gasket so that we can check any shortage with sample itself with the metal gasket. And that will very important that we can remove the additional resistivity in our measurement. And we put the scotch tape on top of this electrode and put another scotch tape covering most of the area of the metal gasket. And then insulation layer, we mostly use the cubic boron nitride with the epoxy mixture. In the Hamlin's lab, we make a further advance that we use soapstone at the center of this cubic boron nitride mixture. So you put the electrode on top of this electrode, and this is a small electrode, not the one whole electrode, but it's a small electrode of 4 areas, and we have the extended electrode to touch the small electrode inside. So, and then this electrode is again held by the scotch tape and crazy glue, so that the important part is that the electrode should not move at all. So it should stay still there, so that we can put the sample nicely on top of this electrode. So this is sample, and then put the ruby side to measure pressure of the sample. And the last part is just squeeze the sample. In this way, you can get very nice electrical resistivity measurement under pressure to check superconductors and other materials. Other methods include high pressure gas loaders. So when you want to load a sample like a gas, like the hydrogen or other light elements, gas materials, you can load with this one. And so you can do the Raman spectroscopy. The diamond anvil cell is transparent, so you can shine the laser in the sample chamber to get the Raman spectroscopy. And you can cool down the whole cell under pressure. And you can do the in situ ruby spectroscopy and Raman spectroscopy in the Hamlin lab here as well. And I think good part is we have access to the large, huge research facilities like the advanced photon source. Thanks to CDAC support, I often go there and or nowadays remotely to do the X-ray diffraction measurement or laser heating and so on. So this is just the illustration how big this facility is. This is the Chicago Cubs, the baseball stadium, Wrigley Field, and then it goes in the advanced photon source. So it's a very large research facility. Now I will talk about the research results. First one is the dense low-G-rich superconductors. So I will talk about the hydrogen-rich. It's not our result, but the motivation, we go to the low-G-rich superconductors. So hydrogen-rich and beryllium-rich and boron-rich and so on. And then we need to ask why we study superconductors. There are very interesting property of the superconductors. First one is the resistivity drops to 0 at the superconductor. So on is discovered in 1911 in Mercury. And not only that, it has also a perfect diamagnet that it expels the external magnetic field. And Meissner discovered in 1933. So these are very useful property of the superconductors. In this case, it's demonstration that tin is in the liquid helium inside and then expelling the external magnetic field, which is, I think, some iron arrow like that. So, and 50 years later, the microscopic explanation of the superconductivity was discovered by the Barton Cooper Sharif in 1957. And the idea is there's a pair of electrons mediated by this lattice and the localized positive charge region. And they undergo the boson-like Bose-Einstein condensate and go through the lattice without any resistance. And this the zero resistivity and then also perfect diamagnetic property gives you a very useful application. And but we need to go room temperature or warm temperature superconductivity to really applicable in real life. So you can change the power grid with the 100 efficiency of the grid, and also you can reduce the cost of the medical equipment like MRI. Also, it can revolutionize the transportation techniques. So superconductor is very useful once it close to the more applicable level. But why we study under pressure? This is a simple illustration that this is from Jim's beautiful periodic table, superconductivity version. That the yellow, the area is the superconductors at ambient pressure, so elemental superconductor without pressure. And there are 30 in this periodic table. And when you use pressure, you will discover more of the superconductors, which are the green area. So 23 more superconductors were discovered by applying pressure. So for example, oxygen is not ambient superconductor, but it's just a gas. But when you apply pressure, it metallize and it becomes even superconductor at 120 GPa. So the oxygen you breathe, the normal life surrounding us, it becomes a superconductor under pressure. That's amazing. And another good part of the using pressure is that the lithium case, you will see the tremendous increase of TC when you apply pressure. When you compare the ambient pressure, TC is 0.4 millikelvin, very low temperature. But when you apply 30 GPa, it increased tremendously to 14 Kelvin. So 5 order of magnitude increased. So pressure can enhance the superconductivity. Then why we study the light element rich superconductors? I'm not saying the only hydrogen, but the light element rich superconductor as a whole. That this is from the Neil Ashcroft, and who is author of this beautiful solid state physics textbook. That he claimed that the metallic version of hydrogen would become high temperature superconductor 1968, and then followed by this paper, the hydrogen dominant or hydrogen rich metallic materials would become high temperature superconductors. So these predictions are based on the BCS theory and the calculation of TC, that this is TC equation, that there's three important parameters, that omega is average phonon frequency, and then the N is the density of states at the Fermi level, and V is the pairing potential. And when you control this, then you will get the high TC. But it's not easy. I'm kind of saying it's an easy way, but it's not easy. You need large phonon frequencies and large electron phonon coupling and large density of state at the Fermi level. But most importantly, it should not at odds with each other. So sometimes kill each other, and that this is the challenge in finding high temperature superconductivity. But the hydride shows a very hopeful picture. That first hydride, superconducting hydride, was the H3S, and then follow-up study showed that the lanthanum hydrogen 10 has very high TC at high pressure. So two groups produce this high temperature superconductivity in lanthanum hydrogen 10. And interesting point is that hydrogen is a cage-like structure surrounding the lanthanum inside. And that's distinct the picture of this system. And this is very beautiful measurement, though it's very difficult experiment. And anything involving with hydrogen is very difficult, in my opinion. And you will see that you need to surround the hydrogen with the lanthanum hydride sample. And in this case, they use a Be₂Re to produce hydrogen source. But overall, they need laser heating and the electrodes, make sure electrodes touching the sample under pressure while laser heating and so on. So overall, the success rate is pretty challenging with this experiment. So one could turn to the other light element like beryllium. So beryllium is number 4, so it's not far from the hydrogen. And lithium case is heavily studied. So, but the beryllium case is not. So we turn into the beryllium case because of the beryllium case is not because of the toxic property of the beryllium. But we have the synthesis team that have expertise making beryllium compound. So we made the beryllium 22 rhenium compound and tried to squeeze this sample. And interesting part is this one has also cage-like structure surrounding rhenium with beryllium. And even better is that it is ambient pressure superconductor. So TC has a relatively high 10 Kelvin at ambient pressure. So yeah, we don't need pressure for this one, but we hope that when you squeeze, you will TC increase like the hydride, but the surprise is that it's opposite. So the pressure kills the superconductivity in this case. So it's slowly going down. We went up to 30 GPa, and TC goes slowly down. And theoretical estimation suggests that the TC will go down, keep going down to 0 at 150 GPa. So this beryllium compounds, so far, we didn't have much success to increase the TC like the hydride. So in this case, we think that the lattice stiffening in this TC calculation case, the lattice constant, spring constant. So, and this exponential term, there's a lattice spring constant, and lattice stiffening under pressure plays very important role in this compound, and which decrease the TC with pressure. And we did a bunch of other beryllium compounds and didn't find, but in the right time, some research group from China, they reported the new diboride superconductor. So first diboride superconductor is MgB2, very famous, and with a relatively high TC, 40 Kelvin, and it has a layered structure, boron layer and magnesium layer. There is two distinct layers. And recently, 2021, Chinese group found the moly diboride becomes superconductor with a relatively high TC, like above 30 Kelvin. And there's a structural transition. There's a buckled layer of boron in the ambient pressure. But when you go to a higher pressure, this is very similar to the MgB2-like structure. So there's a layer of boron and then molybdenum layers. So this gives our attention to the other diboride superconductor candidate. And our theory team, we work with theory and the synthesis and the high pressure team, that our theory team quickly calculate after seeing this result from Chinese group in archive. We searched the other diboride superconductor, and then we found the tungsten diboride. So theory team first suggested that tungsten diboride is a good candidate and in MgB2 structure to have the relatively high TC. And we quickly made this sample in the synthesis team, and beautiful the picture of the sample there. And I took just a small piece of the sample on the surface and then squeezed in the diamond anvil cell. And indeed, we found the superconductivity appears above 50 GPa. And it's not decreasing, but it increases with the pressure. And it keeps going up to 70 Kelvin, which is a relatively high TC in superconductivity, and gradually decreasing afterward. And interesting part is that when you release pressure, we did the releasing pressure measurement, and superconductivity appears at lower pressure. So showing that this superconductivity is metastable. But the theory calculation suggests that they should have the MgB2-like structure, and but the tungsten diboride itself at ambient pressure is not MgB2-like structure. It's right side this figure that it's sp12, which is there's a buckled layer of boron. It's not flat. But theory calculation is the flat boron layer, like MgB2 structure. So at this point, the next step is doing the X-ray diffraction measurement under pressure. Thanks to the CDAC support, we did the X-ray diffraction right away, quickly, and then we find that there's no structural transition. The initial structure, like the buckled layer structure, remains up to 145 GPa. So we don't have any MgB2-like. This is the MgB2-like structure peaks calculated one, and we compare with this, and we didn't find any. But this is ambient pressure structure HP12, and this fits well up to 145 GPa. So we didn't have any MgB2-like structure in the bulk form. So that gives you our idea about the planar defects. The stacking fault or twin boundary-like defects are present in the tungsten diorite. This is our conjecture that under pressure, this layered structure slip each other, and the bulked layer possibly flattened under pressure and giving the MgB2-like structure, in this case here and here, and host the superconductivity. And calculation is here that HB3, the MgB2-like structure, should have the relatively high TC compared with the other structure. So our idea is that we have a fragmentary quantity of superconducting materials in the tungsten diorite, which resembles MgB2-like structure as the planar defects. That's our answer. And then we have the follow-up. We are still doing the follow-up study to prove this conjecture. And other study we did with the dibride is the molybdenite with the other substitution like the niobium. And so niobium is a good candidate for substitution study because this is very close to it's next to the molybdenum, and also niobium boride has the MgB2-like structure, this flat layer of boron and then also niobium. So our hope was that when you put the niobium in the molybdenite, it may stabilize the structure to MgB2-like structure. So pure molybdenite at ambient pressure is this buckled structure. So indeed, we found that the niobium substitution stabilized the MgB2 structure in molybdenite. So we did 10%, 25%, 50%, 75% substitution of niobium into the molybdenite, and all we found that there are the MgB2-like structure in ambient pressure. And not only that, we stabilized the MgB2-like structure in the molybdenite, but also we have superconductivity at ambient pressure. So around 8 Kelvin. When you substitute niobium in the molybdenite, without pressure, you will have superconductivity. And the next step is obvious that we squeeze this sample and to see whether the superconductivity increases or not. But unfortunately, the pressure kills the superconductivity in the substitution study. And compared with the pure molybdenite at 100 GPa, you will see that the pure molybdenite at 30 Kelvin of superconductivity, but our case is around 5 Kelvin. So the niobium substitution suppresses superconductivity in molybdenite. That's what we found. And we didn't have any structural transition in this substitution study. So I want to show the future of the field for superconducting research under pressure, that not only the room temperature superconductivity, but also we should, going forward to the warm TC at the ambient pressure. I think we have a tremendous momentum after the hydride with the TC very high. So I also would like to be the part of this future field that to find the very high temperature, warm temperature superconductivity at ambient pressure. So we have a theory power and the experimental power in our high pressure community. So I think I believe that we will produce at some point the room temperature or warm temperature superconductivity. And now I will switch here to the hydrogen storage research that we use pressure or diamond anvil cell to test hydrogen storage materials. So the barosynthesis means this is Latin for the pressure. So pressure synthesis of hydrogen storage. So why we need hydrogen storage? There is a hydrogen fuel cell already developed, and it produces electricity, turning hydrogen and getting hydrogen in the cell and then turning to the electricity. And then the byproduct of this cell is the only water. So it's clean energy. But the problem is the hydrogen is very hard material to store because of the light element, and also very small. So this is the 4 kilogram of hydrogen stored in this container, and this is just a size comparison. That when you have the hydrogen as gas, and it has a big storage. The problems are the high pressure. We need high pressure and large volume for store gas. That's a potential danger. And we need considerable energy to liquefy liquid hydrogen. And it's not efficient. And we have also heavy weight problem for the metal hydride storage. And also in this case, they have also dehydrogenation temperature is very high. So one could check the light element, and then also people use the graphene to store hydrogen as well, or the fluorine as well. The initial thought is, why don't we use graphite as the hydrogen storage? So, and this is the first postdoc research at WSU with Jinhyuk, and the idea is that graphite is already being used to store a lithium-ion battery, lithium in ion in the anode. So graphite nicely goes in between these graphite layers, and lithium ion is not that small. So why don't we put the hydrogen in the graphite? So that's kind of simple that we can do with the high pressure gas loader, and we put the graphite and hydrogen mixed together in the diamond anvil cell, and did the measurement. And this is the result that you are seeing that the picture is a graphite rich region, and there's a hydrogen rich region, bright area. Graphite is dark, and this is 10 GPa. So in this pressure, the solid hydrogen is already solidified, so above 5.5 GPa. And graphite in this case is very thin, so 1 micron thick. You can measure on the microscope. And so it's 1 micron thick graphite, and there's a ruby, and the pressure medium is hydrogen itself, surrounding the graphite with the hydrogen. And now you are seeing the from upper diamond. This is the picture. And you can do the Raman spectroscopy with this, proving the different region, the hydrogen rich region and graphite rich region. And if hydrogen is in the same condition, should have no difference between this region. But above 5.5 GPa, we see the difference. This is the typical hydrogen vibrant Raman spectrum under pressure. And you will see the distinct peak appears at the 4200 wave number. And above 5.5 GPa, you will see the asymmetric peak appears in the graphite rich region. And when you apply more pressure, you will see the development of tail. And when you apply pressure more at 10 GPa, you will see the small 2 peaks appears in the tail of the hydrogen vibron in graphite-rich region. So what are they? We think they are the stored hydrogen in the graphite, different from the hydrogen outside. And to prove further this idea, we did X-ray diffraction measurement at the WSU, and we found that indeed the lattice parameter of C-axis increase rather than decrease under pressure. So the right pressure at 5.5 GPa, the lattice increases in C-axis. So something goes into the graphitic layers, which is hydrogen in our case. And this proves that the hydrogen can be stored in the graphitic layer. This is the first evidence that we can use graphite as the hydrogen storage materials. And when you estimate how much hydrogen stored in the graphite, this is simply the figure that the carbon rings in the graphitic layer positioning with one hydrogen molecule. And when you calculate this at 10 GPa, the amount of hydrogen would be the 0.2 kilogram per liter. And when you compare with the current DOE target for hydrogen storage for energy application is 0.04 kilogram of hydrogen per liter. So it's 10 times or around 5 times better than the DOE target, but it's 10 GPa. That's the problem. But this opens the way to use graphite as the hydrogen storage. And we can have further develop this graphite hydrogen storage idea for high pressure study. And one could make graphene formation as a bulk that use high temperature or laser heating and so on. And once the hydrogen is stored in the graphene layer, I think there's a more chance to have this graphene formation, graphene with hydrogen attached. So that could be future research as well. And I think this high pressure equipment, diamond anvil cell, can explore these effective hydrogen storage materials. So there are many candidates for the storage hydrogen, like the graphite, as I showed, that also hexagonal boron nitride, the layered materials, 2D layered materials can be good candidate for the hydrogen storage study. And using the diamond anvil cell, laser heating, and also catalyst effects you can study, and also electrosynthesis. So we can do on the diamond anvil cell. To summarize my talk, that pressure can lead us to find more applicable superconductors, and one could eventually to realize the warm temperature superconductivity at ambient pressure. And pressure can lead us to find more effective hydrogen storage materials and lowering the graphite pressure in the diamond anvil cell as the effective hydrogen storage. And lastly, I hope that I show the pressure is a pathway to find the novel materials with unprecedented properties. Thank you.
Thank you very much, Isaiah, for a very clear and nicely prepared talk. That was wonderful. The talk is open for comments and questions. Just unmute yourself or put your comment or question in the chat.
Hi, great talk. Thanks so much. I was actually wondering if you're putting the ruby outside of the electrodes, how is that an accurate measure of the pressure on the sample, and how are you able to kind of calibrate that?
Yeah, so actually the enzymes group, we measure the Raman also, the ruby and Raman, and to compare the pressure gradient. And then also we put the error bar in the case that the Ruby pressure has some error because it's not on the sample, but the side. I think that answers your question.
Yeah, sure, thanks.
Thanks. More questions?
Hi, this is Mo from UIC. Very nice talk. I have a question about the MGB2-like superconductors. So for the other superconductors that kind of produced those like MGB2-like structures, did you also study the nature of their bonding and whether like how similar they were to MGB2? Because for the case of MGB2 like that, the type of bonding, the sigma and pi, that is related to the different gaps. So I was curious whether these other materials also show similar, or like what you can extract if you haven't done like a gap study.
I think the simple answer might be we didn't study that part. Yeah, so I cannot answer quite.
Got it. But can we infer something about the bonding from like what the study that you have done, like amongst the in between the layers and on the layers, like?
I think we did the X-ray diffraction measurement, and we measure the bonding nature because the COA ratio can be changes with the superconductivity, but we didn't find any distinct change in that measurement as well. So I don't know that it has the answer to your question or not, but yeah, that's it. Yeah.
Okay, awesome. Thank you.
In principle, one might be able to see some changes from X-ray Raman of the boron edge. That's a tough experiment at very high pressure, but you might see some changes.
Yeah, that's a good idea.
Roll.
I have one question, Russ.
Oh, okay.
Could you please explain how you loaded the hydrogen lanthanum system? I missed that.
That's not our experiment. That's I'm showing that example of the low G rich materials with the high TC. So lanthanum, I think you're talking
That's
about
right.
this one. Yeah, this one is the other groups that they use the boron as a hydrogen storage and the laser heat and to get the hydrogen and react with the lanthanum. And then I think the right side, they use the lanthanum hydride with the surrounding hydrogen and laser heat it, and then apply pressure and get the TC. Yeah.
Thank you.
Yeah, that's correct. Okay, Roll.
Yes, thanks for the talk, Isaiah. That's very interesting. Just one idea. I'm not sure how to. It's just to something to think about. So, the most abundant form of hydrogen in the universe is actually H3 plus. And not H2 and not H atoms. Because the H atoms, when produced by stars in the flares, produce H2. And there is also H plus. And the reaction H2 plus H plus to give H3 plus is exothermic by about 420 kilojoules and has no activation energy. So most of the hydrogen around in outer space is H3 plus. Trouble with H3 plus is that almost anything will steal a proton from it. That is the proton affinity of anything. You can look these up in Wikipedia, is very high. But so there's a problem. We don't have any complexes of H2 we don't have H3 plus. We don't have compounds of H3 plus, but it's very stable, really. It's also very reactive. It's just an idea that if you perhaps a way to activate H2 is by somehow something that would under pressure generate H plus, or that could possibly, or if not H plus, another, what a chemist would call a Lewis acid, something with an empty orbital, something that's a very good acceptor. Those things will attack H2. So that's, I just mentioned that as something to, graphene is not a particularly good way to activate H2, but BF3, BH3, maybe other kinds of things which have an empty orbital might interact with H2.
Okay, thank you for your comments. Yeah, I will think about that.
That's a very interesting comment, Roel, because there actually is quite an extensive literature of ionized hydrogens at low temperature using different isotopes, in particular tritium.
Yes.
And groups at Livermore decades ago compiled a vast amount of information about the complexes formed in low temperature samples of tritium and deuterium and hydrogen. And you can see evidence for those clusters and the ions stable at low temperature. It's not very widely cited, but there are whole books on this. And I think it shows basically the kind of effect you're describing, but in the pure system of the isotopes.
Yeah, right, right.
More questions, comments?
I had one question on the intriguing this using graphite to store hydrogen. The idea that, do I understand correctly that you need about 5 or 6 GPa pressure for the hydrogen to start to go in to the graphite? Okay. And so do you know anything about, when it goes in and how the amount of hydrogen changes with the pressure? Have you measured that? Can you estimate that?
No, this is our simple estimation that when we have hydrogen in the graphite, then this will have the explanation that the one molecule of hydrogen will be surrounded by this carbon ring. And I think under pressure, the amount of hydrogen, I'm not sure it will change or not, but we are thinking that it stays at the carbon ring surrounded with pressure. So, and we see that above a certain pressure, we didn't see these 2 peaks appearing. So around the 50 GPa, I think these peaks disappear. And at that point, the hydrogen went out. So, but we don't know how much hydrogen will change under pressure in the graphite.
Well, what about when you decrease the pressure? Do you see that is it at all reversible? Does it go out?
I think we did that, and it's reversible. So we don't have hydrogen after 5.5 GPa below that. Yeah.
So when you take the pressure off, then you can see that it doesn't stay at a pressure below 5.5.
Yeah, it's reversible.
Mm-hmm.
Did you try that at variable temperatures? Because at low temperature, you might be able to retain it.
Yeah, we had that idea. I think Jinhyuk has that idea, but we didn't try it. Yeah, at that time. Yeah.
Because if that's true, then you could, in principle, calibrate your Raman peaks or even infrared if you did it infrared and determine exactly how much you have at high pressure. Because you could measure the hydrogen uptake if you could recover the sample.
Okay.
Stefano?
Yes. Hi, Jay. Thank you for the presentation. And now about this letter, so you said the change right when hydrogen solidifies, right? So it couldn't be the change here just due by the fact that you're not anymore in a hydrostatic limit, or because the crystallized hydrogen is just creating a stress on graphite, since when you release the pressure, you go back to the initial condition. So actually you're not intaking anything. Could it be?
Okay. So can you elaborate a little bit more? Yeah, I didn't get quite your claim.
So basically you have here graphite and you are squeezing it with hydrogen.
Mhm.
I don't know the hydrostatic limit of hydrogen, but you see a change in the diffraction when hydrogen crystallizes. So you're changing the condition. Probably you're not anymore in hydrostatic condition, and you are crystallizing your pressure transmitting medium. So I don't know if the changes in the diffraction may be due to the external stress given by the crystallized hydrogen, or the loss of hydrostatic condition, and not from an intake of the hydrogen in the structure.
Yeah, our Raman spectroscopy tests that we have some, shows that the hydrogen goes into the graphite with the distinct peaks, different from the pure hydrogen. And at the same pressure, we see the diffraction pattern that the C-axis increases. I think it's strong.
Yeah, but that could be also given by an external stress, not necessarily by an intake.
Yeah. Okay. Yeah.
But when hydrogen freezes, it's actually a very, very weak solid.
Mhm.
Mm.
And you can measure that stress.
Right. It's okay.
And couldn't you maybe repeat the same experiment with helium that you know that has a hydrostatic limit up to 40 GPa, and probably should penetrate graphite easier than hydrogen.
And this solid case, it's the dynamic, the distance between two hydrogen is the two hydrogen molecules getting smaller compared with the gas hydrogen. And I think at some point at pressure that it fits with the graphitic, the layer distance. And I think that's also another explanation that the solidifying hydrogen can be stored in the graphitic layer, the space. Yeah.
Mm. Okay. Thank you so much.
Thank you.
But has the equivalent experiment been done on helium to see if helium has the same effect, that it causes graphite to expand at some point? Relative to...
I don't. I think my research was focused on hydrogen and graphite. Yeah. So.
Right. There's a question about the density of solid hydrogen at 10 GPa.
Yeah, I think that's the well known from the literature, and I think we put the number in the paper, but I don't have number in mind. Yeah,
It's something several groups, including ours, worked on in the late 80s. So they're
right.
Would like to follow up with me. Okay, any more questions? If not, thanks very much, Isaiah. Very nice talk. Great to see everyone again.
Thank you.
We'll see you at the next webinar.